Good morning. Thank you for inviting me to this, the 12th conference on data envelopment analysis of Iran. Iran is a country from which I have had the opportunity to have both co-authors and PhD students, and continue indeed to work with them. The presentation will cover the regulation of utilities and the use of data envelopment analysis in the context of regulation. I will briefly cover why it is necessary for data envelopment analysis or other efficiency assessment methods to be used in regulation, what the aim of the regulator is. I'll briefly use the case of German electricity distribution and gas distribution companies, their regulation, as an example, and I will end up with a paper in which we propose a method for incentivizing regulated companies to reveal efficient practices. The method is, of course, based on data envelopment analysis. Coming to why regulation is necessary in the case of companies such as water, electricity, gas, and so on, utility companies. The answer is because such companies have very expensive and long-living assets, and each customer of these companies is only connected to one company, one water company or one electricity company, so far as the actual wiring or piping is concerned. Therefore, that company enjoys a sort of monopoly power. So therefore, normal competitive forces that would make companies reduce costs do not operate very well with companies that enjoy monopoly power. And the regulator has been set up there by governments in order to mimic competitive markets, so that the companies will have control on their prices, so that in order to then make a profit, if their prices are controlled, they would have to become more efficient. So that is the idea of the regulatory process. And for the regulatory process to operate, it is necessary to assess the levels of efficiency of companies, and that is where data envelopment analysis fits. Now, I will, as I say, use the German example where DEA is used in the regulation of gas and electricity transmission companies. And I will explain how, in their case, DEA is used. Schematically, what happens is the regulator at a certain point in time runs an efficiency assessment. In the case of Germany, they use DEA, but also stochastic frontier analysis as two separate methods, and they then adopt as the efficiency for the company the best that results between those two methods, DEA and stochastic frontier analysis. And suppose you have a company whose cost level is inefficient because the efficient level is somewhere down there. Then the regulator would set a revenue target for the company, which in effect would mean the prices are controlled. It's set in the form of a revenue target running until there is another assessment of efficiency, which might be something like 5 years away. So the efficiency gap that exists between the actual cost level and the efficient cost level, it will be the regulator's intention to force the company to reduce that inefficiency gap, maybe not go all the way down to an efficient level if the efficiency gap is too large. But if you notice also, the actual efficiency level, the target, if you like, is actually not maintained at the place it was found at the initial assessment, but going forward, there is a suggestion that the management practices would change, the technology would change, and so the efficient level of cost would actually itself be going down. And so the company, which was inefficient, would be having two components to its inefficiency to cover. One is its own inefficiency, and the other is also the efficiency gains that will be proving necessary because there is an expectation that the efficient benchmark, the efficient boundary, will be actually improving over time. Costs will be going down because of improvements in management practices, and also the technology itself will be changing. In the case of Germany, DEA, which I assume you're all familiar with, requires an input-output set. In the case of Germany, the input is total expenditure for transmitting the gas or the electricity. That total expenditure consists of operating expenditure, day-to-day expenses, staff and materials and so on, but also capital expenditure. And the capital expenditure needs to be depreciated over time because the assets, as I said earlier, live a long time. So there are two different methods of depreciating the assets. One is by historical depreciation costs, which differ in companies, and the other is a annuity, which is calculated average cost by the regulator for each type of asset, by assuming a certain lifetime for the asset, and then applying an annuity, a depreciation, if you like, but which is constant over time. And so that takes care of the input. So far as the outputs are concerned, you have there on the screen the outputs that were used for the regulatory period covering 2009 to 13, and the more recent one, 14 to 18. And as you can see there, what you have are the number of connections, the number of meters, the length of cable for low voltage, cables for medium voltage, lines for medium voltage, and so on. Also the difference, the peak level, the peak load of electricity or gas consumption. So obviously I'm not going to a justification of how these were arrived at. Suffice it to say that there would have been many consultations within the industry as to what would be the outputs that would reflect the drivers of expenditure that is being modeled. Those drivers, by the way, include renewable sources of energy such as wind power. And the assessment is run and the efficiencies are determined at company level and also, as I mentioned earlier, at efficient company level, so to estimate the efficient boundary. And then the regulator uses a formula to set a revenue target for each company. That is, what is the upper limit of revenue that the company could have in each one of the years T. That's based on the expenditure it had, the non-controllable expenditure, the controllable expenditure. But where DEA fits is this one's highlighted in red. This here, VT, is a proportion of the inefficiency that would have been found by DEA. And so if you subtract from one the level of efficiency, you have an inefficiency level. And so that inefficiency, or rather the inefficiency is subtracted from one to add to the costs. So the efficiency level is taken into account in setting the revenue target. And also this part, which is what we call the boundary shift, that is efficiency gains that would be expected from the industry as a whole, because the efficient boundary would be improving. And that results in a sort of glide path of efficiency savings. So you have for each company, the revenue that is permitted consists of, initially, it has the non-controllable costs, which the regulator allows to be carried forward, the efficient cost level, which has been estimated, but the inefficient costs are gradually reduced, or the revenue cap is set so that the inefficiencies are gradually reduced. In this particular schematic representation, the inefficiency is eliminated altogether, but in other cases, actually, some inefficiency would be allowed to be carried forward. If the original inefficiency gap was very high, the regulator wants to make sure the company survives financially. And so it may permit some inefficiency, giving more time, in effect, for the inefficiencies to be eliminated. So that's the system that's operating. And what I want to present to you now is a method that Mohsen and Heinz and I have put forward. It's appeared in the European Journal of Operational Research. The DOI link to it is there. And what we propose in this paper is a method which would incentivize companies to reveal efficient practices, so which the regulator can over time incorporate in the revenue cap formula. We start off with the motivation that was drawn from work done by Peter Bogertoft and Per Agrell some time ago, where it was suggested that essentially the regulator has an asymmetry of information in that the regulator cannot micromanage the companies. The companies know how it is most efficient to operate. The regulator can only deduce efficient practices by running comparative efficiency assessments with DEA or stochastic frontier analysis or other methods, and identify the more efficient companies. However, the more efficient companies have a moral hazard in that if they reveal efficient practices, those efficient practices will be incorporated by the regulator into the revenue cap formula, so that next time around there is an efficiency assessment, already efficient practices will be known and the regulator will be asking for more efficient savings. So there is a disincentive for companies to reveal efficient practices. And what Peter Bogertoft and Per Agrell suggested was that actually, if we were to use super efficiency as a concept, which I'll explain in a moment, and then run a formula of this type where the cost C star that the company is permitted to recoup through prices would be equal to the cost it had initially, plus some proportion rho of its efficiency theta minus 1. Now, if the efficiency runs from 0 to 1 only, then theta is 1 or below. And so whatever the value is of rho here, let's assume rho is 1 for the moment. When theta is below 1, the efficiency level of the company, then theta minus 1 will be a negative value. And so you have a negative proportion of the cost added to the initial cost. In other words, you are requiring the company to make a saving. And that's how it is generally. However, if you change the form, if you estimate the efficiency not 0 to 1, but permit super efficiency so that theta can go above 1, then this component here becomes positive. And so the company suddenly likes to have as high a value of theta as possible, so that it will be permitted to have even higher costs than it actually incurred, which would be profits for the company. So that's the general idea. And the company, as I was saying earlier, would have a disincentive to reveal efficient practices. In this schematic representation here, in order to explain the method, the current method as it exists at the moment, where you don't have super efficiency into the formula, but only efficiency, if you have cost and just two outputs in order to illustrate the method, you have the efficient companies that are giving maximum output levels per unit cost. This graph relates to unit costs. Then any company that is found to be inefficient, essentially, if it maintains its output levels to where they are, it would need to reduce the costs in order to reach the frontier. And that would be the efficiency savings that are required of the company. So it has no incentive to reveal, particularly the companies that are there on the efficient boundary. They do not have an incentive to reveal at all more efficient practices, because all that will happen is the boundary will go to an even more efficient place. So the Peter Bogertoft idea is to assess super efficiency and then apply the revenue cap. What that means, suppose you have companies that include E, D, and C and B here. In that case, for company D, if you assess it, it would be efficient and the boundary will be running both the black part and the green part, like that. But under super efficiency, you would assess company D against the rest of the companies. So you assess it against the frontier drawn on the rest of the companies. So FD reflects the super efficiency of the company. Its super efficiency is OD divided by OF, and that would be above 1. So the theta value will be above 1. So companies like company D, but the same would be with company E. If you assess it relative to the rest of the companies, the frontier would go down here, so the company would appear super efficient. So they would have theta values that are above 1, and so they would have an incentive to reveal efficient practices, to become even more super efficient, because the benefit they get here, this positive component, is larger, the larger the theta value. So the Peter Bogertoft and Paragrell suggested this idea that we use super efficiency in order to set the efficiency targets for companies. And what we propose is to actually include even more companies into this framework of super efficiency by drawing the boundary a bit closer in than the original DEA efficient boundary. So the question is how to draw the boundary closer to have more companies appear super efficient. And what we propose is this. We propose that you run, first of all, a DEA assessment, a normal DEA. This is a normal output maximization DEA model, in which you maximize priority phi to maximize the observed output levels, while the input levels, which is the cost, are not exceeded. So it's the standard constant returns to scale DEA model to estimate the efficient output levels for each company through this formula. So these are the DEA targets, if you like, on the outputs. And they are denoted by Y tilde on top to distinguish from the original observed output levels. Now, once you have these output levels, you can run a linear programming model of this type here, where you estimate UR costs per unit output, but you use for outputs the target levels of each company, the Y tildes. So what you have here is you're solving a DEA model, sorry, not a DEA, but just an ordinary linear programming model, in which your decision variables are the unit costs per unit output. The outputs are the efficient output levels of each company J. So you're saying minimize the aggregate cost across all the units in the set from 1 to n by using unit costs per unit output, but the outputs are to be those of those that are efficient for each company. So in effect, schematically, what you're doing is you're reflecting all these units, all these dots that you see, onto the efficient frontier. They're all reflected there. And because you have this constraint that says for each company, the aggregate cost cannot be below the observed cost, what in effect you will do is you will estimate unit costs which would define an efficient boundary, efficient quote unquote, which is EB in this case. You would be enveloping the efficient boundary from below. Now this would give you, this would make all these companies whose original outputs, not their efficient, but the original output levels, place them above the line EB, would appear to be super efficient. And in one sense, you could actually stop at this point and say, right, so this puts a lot of companies into the super efficient level, and therefore this would give these companies incentives to reveal efficient practices. However, because this efficient level EB will depend very much on how many extreme companies you have, extreme in the sense that they're only good on one, either on output 2 or on output 1, but not generally good, efficient. So in effect, this would present too many companies as efficient. So you want to improve on the efficiency level. And one way to improve on the efficient level is to use clusters of companies so you can come closer to the original DEA efficient boundary. And the way to do that is to use a variant of this linear programming model, which instead of determining a single set of unit costs for the outputs, would determine different unit costs for different clusters. So you would solve this linear integer programming model, which is the same as the model I had before. So it too determines unit costs U, but notice I have two subscripts now for the unit costs, UKR, because the R defines the output, as it did in the previous model, but the K defines a different cluster. So I need to decide in advance how many clusters I would have, 2, 3, and so on. The capital K is the number of clusters that the user would decide upon. But once I decide on the clusters, I construct this model, which is very similar to the one I solved before. So I minimize the aggregate cost ER, efficient revenue, efficient costs, across the whole set of units. So minimize the sum UR. The UR, because I'm minimizing here, this inequality will always be met as equality. So at the optimal solution, that is. So I'm minimizing the aggregate costs across all the set of units, estimating unit costs, UKR, a different unit cost for each output, but also for each different cluster. Each unit can be allocated to only one cluster, and that's where the 0, 1 variable delta kj comes in, so that delta kj is a 0, 1 variable, and the sum of the delta kj's across the clusters is equal to 1. In other words, each company j can be only allocated to one cluster. Schematically, when you solve this model, you will end up with a graph that looks like this. If I have only two clusters in the graph that I had before, and solve the model that I just showed you before, it would determine two clusters. One cluster would have efficient costs that lie on the line ER, and another cluster that would the units that would have efficient costs that lie on BR. Now, with these as locations for efficient costs, it would mean I have reduced the number of super efficient companies. It would be only companies like D, and any companies that I have just above these two lines, ER and RB. The two lines needn't meet, by the way. You could have the clusters end up in different places. And the idea is that you lower the benchmark so that more companies will appear super efficient and therefore will be incentivized to reveal efficient practices, but not too many companies. So it's a balance. The more the clusters you define, the closer you can get to the DEA original efficient boundary. But of course, then you have fewer and fewer companies that would be incentivized to reveal efficient practices. So there is a tension between how many clusters you define on the one hand and how many companies you incentivize on the other to reveal efficient practices. In the original Peter Bogetoft ideas, you could only have companies like E, D, C, and B, which were DEA efficient originally. They are the only ones who could potentially be super efficient and therefore reveal efficient practices. Whereas in the method we are proposing, you have more companies that could be appearing super efficient and reveal efficient practices. And the more the clusters that you define, the fewer the companies that would be super efficient. I'll illustrate to you with an example that we run with 400 banks, not regulated companies, but it's the same idea. We had input total costs and the number of outputs of the banks, the total number of deposits, the loans, earning assets, and so on. In this case, when you run the DEA model, if you look at this column here, where you have indicatively K as many as 400 clusters, in fact, the original DEA model, you estimate the efficiency, the median efficiency, to be just short of 80%, and something like 21% is of the aggregate costs can be saved by the banks, of the aggregate operating costs. Now, if you adopt the first model I presented, where you enveloped the efficient units with a single cluster, K equals 1, the median efficiency jumps from 80 to 90%. That's the efficiency, but the actual aggregate costs that could be saved are only 14% compared to 21. So in other words, the boundary has moved closer to the operating companies, and it would reveal quite a few companies as super efficient. In fact, you can see 16%, that's 65 companies, appear as super efficient. If you raise the number of clusters to 2, then that drops from 65 to 26 super efficient companies. And now, instead of 14, you can ask companies to save, or banks to save, 18% of the aggregate costs. And as you increase the number of clusters, you see you're getting closer and closer to the benchmark cost of 21% that could be saved. So in this particular case, for example, with 2 or 3 clusters, you are getting very close to the original DEA savings that you were estimating. So you are close, the benchmarks are close to the DEA benchmarks, but the advantage is that you have, instead of no super efficient company, you have 26 or 13 companies that would be incentivized to reveal efficient practices. They would be sharing something like 5% or 3% of the total operating costs across the system as incentive to save. So I hope I have not exceeded my time too much. To conclude, DEA is highly integrated in many regulatory systems, especially in Europe, but across the world as well, Latin America in particular. DEA is used to estimate efficiency savings at company level, which are then integrating into the determinations the regulators make into the revenue cap or price controls, so that companies are forced or incentivized to make savings. The paper I presented shows an approach where companies can be incentivized to reveal efficient practices by allowing them to set prices or to have revenues which incorporate a proportion of the super efficiency they have. And in order to have super efficiency, you have to, you of course can use the super efficiency where you exclude just the one company at a time from the system and assess it relative to the best of the rest. But you can also use the approach that I presented where you can use clusters of companies to draw a new efficient boundary instead of the original DEA, which you can control how close you get with a new efficient boundary to the original DEA boundary by increasing the number of clusters. I should end up by saying efficiency analysis is an ongoing journey. It's integrated, but it's evolving over time, and a key objective is to keep learning and share best practice in regulation across the world. Thank you very much, and I hope to be connecting live during the presentation if there are any questions. Thank you.